Okay.
How was your weekend?
Too
Like
short.
how was it?
Too short. Too short.
Yeah.
Too short. Um.
For us, it's only like 8 weeks left. 8 weeks?
Eight plus 17.
Yeah. No, 8 weeks and 3 days.
Hmm?
8 weeks and 3 days.
Oh, cool.
Decay. All right. Let's have a look here. Come on. Wake up. Here we go. All right. So, like I said, the last part
Okay.
we're going to have a look at is the atom. Got that, KJ? Yep, got that? Right, so um, there's not much talk I need to do about the atom because you all know it very well from chemistry. Okay, so there's not much background information to give that you wouldn't already know. And we kind of talked a tiny bit about it already with protons, electrons, and neutrons. So you already have enough really to have a start at the atom. So we have this thing called radioactive decay, which we can have with atoms. It's also known as nuclear decay, but we call it radioactive decay. Or radioactivity. It's the process by which a nucleus of an unstable atom loses energy by emitting ionizing radiation. So some atoms lose energy as time goes on, and radioactive decay is how they lose this energy, and they lose it by emitting uh, radiation, which we haven't even said exactly what radiation is, but the key idea here is radioactive decay is atoms losing energy by this process. A material that spontaneously emits such radiation, which includes alpha, beta, and gamma rays. I probably should fix that last sentence there. The last point I'm just making here is that we give, or we say that there are three types of radiation that come out from this decaying atom called alpha, beta, and gamma. So when we have a material that is losing energy through this radioactive decay process, it can lose it by three ways: by alpha radiation, beta radiation, or gamma radiation. Got that? Yeah?
Last sentence.
Okay. The last sentence should really say there are three types of radiation: alpha, beta, and gamma.
Yeah.
Yeah? Okay. Okay, great. Alright, so for example, we have this material called uranium-239, and it's an isotope of uranium. Um, and you should already know what isotopes are from chemistry. It's radioactive. It's an example of a material that's radioactive. This means it will decay. That is, alpha, beta, and gamma radiation will be released from it. Note that uranium-239 will not do this forever. So you have uranium-239, and there's alpha, beta, and gamma coming off of it, and it's not going to do this forever. It releases the radiation for a certain amount of time only. For some materials, this is a very long time, and for some materials, this is a very short time. Uranium-239, I believe, is quite long.
It depends on what.
It depends on how unstable the material is. So, it also depends. It even depends on things like temperature. So, for example, you all learned about the Chernobyl disaster in high school. Do you know Chernobyl?
But generally,
Or even not Chernobyl, but in the well, no, you should know about Chernobyl. Do you know about Chernobyl? It was a nuclear power plant disaster in 1980 something. I don't remember when. Anyways, my point is, the ground is now radioactive from the disaster, but actually because Chernobyl is quite a cold place, it means it'll be radioactive a little bit longer. So temperature and many other things affect it, but usually it's whatever. It's usually something about the material, but even things like temperature can affect it, and also many other things as well. But it's a feature of the material. So I think uranium-239, I can't remember right now, but I think it's one of the ones that is quite big. Like some of them will be hours, some of them will be years, some of them will be seconds. I think uranium might be in the scale of years. I know, for example, carbon-14, which is radioactive, is on the scale of thousands of years. But anyways, that's more about that's in another class. Right, so as I was saying, there are three types of radiation. So the first one is alpha particles, alpha radiation. So alpha radiation is basically two protons and two neutrons. Now, you should know from chemistry, two protons make. What do two protons make? Make helium. So in fact, alpha is really just helium, except it's helium with no electrons, just two protons and two neutrons, no electrons. So what's its charge? Positive or negative? What is it? Come on, Wiki. Positive. Yeah? Two protons, two neutrons, no electrons. Its charge is exactly positive 2. So there's nothing really special about alpha radiation.
How do the materials how can they pass?
Oh yes, we'll get to that, yeah.
It's what?
The properties of each. Okay, so just a quick drawing here. So what I mean here is you've got your radioactive material, and there's radiation coming off of it, and it comes off in the form of alpha, beta, or gamma. And all alpha actually is this radiation that comes off. All it really is just two protons and two neutrons. So in other words, it's a helium particle. Helium 4-2. Two protons and then two protons and two neutrons. Sorry, two protons and two neutrons. So 4 nucleons altogether. Two protons.
2 protons
and
and
2 neutrons. No electrons. So that means this alpha particle has a charge of plus 2 times um, whatever it was, 1.6 times 10 to the minus 19 coulombs. Anyways, it has 2 E's. Okay. So that's alpha. So that's nothing particularly special. Oh, I should also say that these particles are moving very fast as well. So this has a great deal of kinetic energy. Right, so beta particles. So what type of particles are beta particles or beta radiation? Well, beta is even less special. Uh, all they are high energy, high speed electrons. So really just fast electrons.
so their charge is -1.
Hmm?
So their charge is -1.
Yep. Yeah. -1 charge. Got that? Yeah. Okay. And finally, gamma radiation. So gamma radiation is the only one which is actually not a particle. So it's also known as gamma rays, and it refers to electromagnetic radiation of high frequency. So in other words, gamma is just an electromagnetic wave with really high frequency, higher than X-ray. Um, it's right up there, not the highest frequency, but a very high frequency. Got that? Yes? Yep. Okay, so when radioactive decay takes place, so you have your material, uranium-239 or whatever it is, and you have particles coming off, and you have electromagnetic radiation coming off.
Does it have to be like three ray levels? Can be only one, two, like only gamma, only alpha, only beta, or like three levels?
Um, I think I don't know if it has to be all three. I do know that it could be something like most of it is this and a small amount of it is this. So we can say in some cases it might only be alpha, but I'm not sure if technically you get all three, you know. But in some situations it might be that there's so much of one compared to the other that you can just consider only that one. But do you have to have all three? I don't think you have to have all three. But no, you don't have to. It could just be one of them. But I think usually they go together. Usually you get all three, just maybe in different amounts of each. Okay, so when you have your decay, so for example this is mass m and then there's a small little m coming off here. There are 4 things which are conserved. Some of this you would know already from mechanics. So the first thing is energy.
You put m like it is
Say again?
the m.
What about the m?
stands for?
What do you think M stands for?
Math.
Well, very good. I see the break hasn't been that long. So there are four things which are conserved. The first one is energy, and you know this from mechanics, conservation of energy. So the energy before the decay takes place must equal the energy after the decay takes place. The second thing which is conserved is momentum. So the momentum before the decay equals the momentum after the decay. The third thing is charge. So if this has a positive 2 charge, then that means this one lost positive 2 charge. That the total charge is still the same. So whatever charge this has, it means it came from the original. In total, the charge is the same. And the last thing is nucleon number. So I want you to write these 4 down. These are the 4 things which do not change after decay takes place. Got this? Yep. Yep. Okay. Lol. I don't know the questions here. That's okay. I'll just make one up.
Don't need to.
Huh? I know I do need to. Let me just fix this first one here. Okay, so I don't think. Do you know what? Actually, I think I'll just let me have a look here. Yeah, in this one here, I think it was the next one that I had. Let me just check. I had more maths in it. So the first one is more just ideas. Let me just check something here. Yeah. Okay, so I'll just type in some questions. So let's see. So we haven't done too much yet since we just started. All we really have is alpha, beta, and gamma radiation. Just the definitions, yeah. So maybe this is why I had trouble thinking of a question. That's really just definitions. Alpha, beta, gamma. Well, maybe I don't want to have any questions. Let's have a look. Maybe we'll do an exam question. I think that'd be good. Physics. Past exam papers, past exams, IFY past exams, physics 2015. Okay, so let's see what atom question we had last year. Yeah, this is more later in the chapter. Okay, I know what I'll do. Right. I just need to get the mass of uranium-239, but we'll do something like an an atom of uranium-239 emits an alpha particle. So I'll give you this one to try. It can be a little bit of a revision question from mechanics. So I just need to get the mass for uranium-239. Well, if you have 1 mole of uranium-239, what should its mass be? So this is chemistry knowledge. No, I just want the number. Don't want the sentence. If you have a mole of uranium-239, what's its mass? What the heck is 239? There's a unit in that, isn't there? What's the unit? Grams, thank you. So the mass should be 239 grams. Yeah. So let's say an atom of a mole. I'll make it easier. A mole of uranium-239 emits an alpha particle with velocity. So usually the particle is moving quite fast. So we often give it in terms of c. So for example, a beta particle would be like 0.7 c. So I'll say an alpha particle. We'll say 0.1 c. So a mole of uranium-239 emits a mole of uranium-239 at rest emits an alpha particle with velocity of 0.1 c. What is the recoil velocity of the uranium-239? So what's happening in this picture, if you look, you have the uranium-239, and then an alpha particle is released, and when the alpha particle is released, the uranium-239 moves backwards a little bit. This should remind you of what problem in mechanics? Yeah, but in particular, which example? Yeah, but in particular, which example in collision? The gun, yeah. With the gun and the bullet that's released and the gun moves backwards. Yeah? So I want you to try this one. You already know the mass of a mole of uranium. What is it? It's 239 grams. Now, the mass of helium is roughly equal to the mass of 2 protons plus 2 neutrons, which is the same thing as roughly the mass of 4 protons, which is on your calculator. It's constant number 1. So its mass is roughly 4 of these.
Mass of
not
helium
n mole, a mole.
Yeah.
helium is 4 grams.
Say that again?
Mass of helium is 4 grams.
No, a single helium atom, not 4 grams. They would be quite painful when they hit you in the face. You know that's way too big for a mass of helium to be 4 grams.
Has that?
No, what? No.
Yeah. Now think about what you're saying.
No, I'm talking about this.
A mole of uranium-239 has mass of 239 grams, roughly. It's not exact now, roughly, which is at rest. Then emits an alpha particle with velocity of 0.1 c. What is the recoil velocity of uranium-239? Assume the mass of the alpha particle is roughly 4 times the mass of one proton. Now, again, I'm saying roughly. It's not actually exactly that, but for the moment, we'll take it as that. Okay, I'll give you a minute to try this one. I'll need my calculator too.
What's the mass of one proton?
It's on your calculator, it's constant number 1. You got your calculator? 1.67 times 10 to the minus 27.
Grams.
Yes.
C is the speed of light. That is 300.
That's the speed of sound, dude.
Sorry.
3 times 10 to the 8th. You finished correct. It's a mechanics question, collisions.
What are supposed to find again?
Recoil velocity of the uranium.
It's 1.9 times 10 minus 10.
I have to work it out. It should be small.
I got 8.38 times 10 to the minus 22.
That's really small. It could be that. We'll have to have a look.
We forgot the period.
I know. I'm trying to think of some questions for you to do.
No, this is
Okay, let's have a look at this question now. Right, so this is just a straightforward mechanics question. You have your uranium here of 239 grams, and out comes an alpha particle, and its mass is 4 times 1.67 times 10 to the minus 27 kilograms. So this is 0.239 kilograms. So conservation momentum, M1, that's right, you mixed up your grams and kilograms, didn't you? M1 U1 plus M2 U2 equals M1, right underneath, equals M1 V1 plus M2 times V2, which I said was, what did I say was a tenth of the speed of light, was it?
Yeah.
0.1 times 3 times 10 to the 8th. Alright, so you're just solving this equation for V1. Nothing special there. Four times. Okay, so you get a very small 8.38 times 10 to the minus 19 meters per second. Yeah, did you get that eventually? Yes, okay. Can I go back? Okay. Also, you could have changed the mass of the alpha into grams, but it's we changed both into kilograms anyways. Can I go back? Okay, so let's see, what other type of questions do we have? I'll give you another one here. Yeah, actually, you know what? I think we should do a question where you have to balance it, but I need to get a formula from online. Okay, let's put in another question. Right, so you've done balancing equations in chemistry, haven't you?
Yeah.
Balancing reactions, yeah? Yeah, well, actually, let's do the example with the uranium for a moment. So, with the uranium, what you can write is uranium 239, and down here, oh actually, do you have a periodic table?
Yep.
Yeah. Have a look at what uranium is.
Is that example or?
Yeah, my example.
The uranium should be 240.
No. No. 92.
92.
No.
42.
What do you mean no?
What is this? Oh yeah, 93.
Okay. So my question then is, when uranium 239 decays, it changes what it is. So when you think about it, alpha particles are what? 2 protons and 2 neutrons. So where did these protons come from? They came from the uranium. So when the uranium decays, it changes what it is. It is no longer uranium 239. For example, when uranium 239 emits an alpha, it becomes, I think it's thorium. Can you give me the periodic table there? Where is it? Where was uranium here?
258.
There it is, yeah. So you see just to the left, 2 places to the left of uranium is thorium. Yeah. It becomes thorium. So the equation for that
Loses 2 neutrons.
loses 2 protons. And the reason for that, if you think about it like this, here we have 92 protons. Yeah? That's what uranium, it's in your periodic table.
It's 232.
Dude, it doesn't have 232 protons. You know this. You know this from basic chemistry. Don't you? Yeah? How many atoms are there in the periodic table?
90 something.
Yeah, so like the most is 90, whatever, 92 protons. We can't have more than this. So there's 92 protons here. So if your alpha radiation has 2, that's because, or I should say, because it has 2, that means what's left must have 2 less. So this has 2 less than 92 because it gave 2 of it to the helium. But notice that on the bottom we have 92 protons on the left, and on the bottom on the right we still have 92 protons. Actually, that's not 239. That should be 235. And here we have 239, but here we have only 235, and this is because it loses 4.
Right.
Because it gave the 4 to the helium.
Okay.
You get the basic concept here? Yeah. So the uranium gives two of its protons and two of its neutrons to the alpha particle. So what's left has four less. So 235. So it's no longer uranium, it's thorium. Okay. So my question then, um, the equation would be, so we had uranium 92 and 239, and that became thorium 90 and 235 plus your alpha particle. I'm just typing in what you wrote down. What would be the equation for uranium 239 atom releasing one alpha and one beta particle? So what I want you to do is make this equation again, except this time the uranium releases an alpha and it releases a beta. And also, which I've not told you yet, which I'll tell you now before you write the equation down. Wait, before you do it, there's a key piece of information you need to have. When the uranium 239 releases an alpha, this alpha has two protons and two neutrons. So here this loses two protons and loses two neutrons. Does that make sense? Now, for a material like uranium 239, it releases a beta. So what's a beta? Yeah, so this one here is one electron. So here the uranium 239 loses one electron, but also something else very strange happens. I don't know if anyone knows this from high school. What happens as well is that one of the neutrons becomes a proton inside here. So one of the neutrons becomes a proton inside the uranium. So literally one of the neutrons converts and becomes a proton.
Yes. That's why the beta is B01.
Yeah, well, we won't worry about the symbol just for the, well, okay, if you want to, you can. The beta is an electron. Do you know the chemical symbol for the electron? It's E, what's at the top here? How many neutrons are there in an electron?
0.
Correct. And here we have to put a -1 because it's to keep the equation balanced. It doesn't have any protons. If anything, it's missing a proton. It's an electron. It's like the opposite of a proton. So that's a symbol for a beta particle, an electron, E0 -1.
Should we use the symbols X and Y for the elements it's going to turn to? Like
No, well, what I would like you to do, you can use X for the moment, but what I'd like you to do is try and use your periodic table to figure out what the element is. Now, it should be near where uranium is on the table. Do you have the periodic table? You have chemistry today?
Yeah, we have
Yeah.
exam today.
Not today.
Today?
today.
Chemistry exam.
Yeah.
Try this one, try this one.
No, it's not today.
It's on Wednesday.
Please check your email.
It's on Wednesday, but
It's on Wednesday.
4th of April.
No, man, it's
6th
not
of
today.
April.
6th of April is the math assignment due date.
Check your email.
Just try this one, then you can check. Okay, you got this one finished? I'll try and find some more equations to balance. Did you look up the periodic table for what element it should be? Is that a no? Please look it up. Question?
No.
Okay. No, you don't have to completely seal us in, thank you. Right, let's have a look at this now. Okay, so we start off with our uranium 239 and 92. So we know that we have an alpha and we have a beta. So the alpha, that's helium 4, 2, and the beta, that's an electron with E0 minus 1. So the question is, what must we have here to keep it balanced? So we know that, yeah, it should be 92 should equal the bottom number plus 2 minus 1. So this number here should be 91. And then on the top, this here should be 2, well, it has to be 235, because 235 plus 4 makes 239. So if you go to your periodic table and look up what has proton number 91, protactium. Wow. PA. So we have our equation U92 239 PA 91 235 plus helium 42 plus electron 0 minus 1. So that's the equation for the decay here. Our uranium becomes this protactium, blah 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 blah, protactium plus an alpha plus a beta. Actually, this question here is quite a common exam question, so I wanted to try and find some practice online, because I see these ones, they come up maybe every, well, I'd say they come up maybe 90% of exams. Let's find some. Let me just close this.
And they give the periodic table for it?
No, they won't expect you to look it up in the periodic table. They'll tell you what the missing element is. Right, so I'll just type in balance nuclear equations. I suppose it's chemistry-ish. In fact, I would say the current person writing the physics exam, he always puts one of these questions in the exam, and sometimes they're in A and sometimes they're in B, but it's a pretty, balancing the equation is pretty easy, because all you have to do is literally make sure the top total is the same on both sides and the bottom total is the same on both sides. So provided that you can count, you should be okay with this question. I know, it's a bit iffy, but you should be okay. Come on, open up. No, of course not. There we go. Let's see if these got good questions in them. Okay, the first couple, we can try the first couple. So, you'll need, for these questions, you'll need your periodic table, okay? So, the alpha decay of radon radon 198, and then the beta decay of uranium 237. Just the first two, please. First two.
Radon 198.
Radon 198 and uranium 237.
That is what, alpha or beta?
Huh?
Oh, alpha.
Yeah.
Which one is the alpha?
What?
Which one?
Dude, it's right in front of your eyes. Radon is the alpha one, and the beta decay of uranium 237. I'll copy them over here. The alpha decay of radon 198 and then the beta decay of uranium 237. Sorry, you got those two? So it's radon and uranium 237, the beta decay of that, of uranium 237. Do you need to get the question back, Tekken? It's uranium 237 beta decay. Uranium 237 beta decay. You got those two done?
Yes.
Okay, let's have a look at them. So the first one, what was it?
Alpha decay of
Last
is
one.
Radon
198.
198?
Yep.
Yeah? What's the proton number for radon 198, or just radon?
Eight.
86.
Yeah.
So there's an alpha, so that's helium 42. So that means well, it's not radon, it's something with number 84. What's that?
It was polonium.
Polonium.
Yeah.
And the number here is 194.
Yeah.
Okay, and the next one is uranium 237, is it?
Yeah.
And its number?
237.
No, the 92, isn't it?
Yeah.
And it's a beta, so that's an electron with 0 minus 1. So in this one now, this is the weird one, where one of the neutrons becomes a proton. So what happens to the number of protons? 93. And what do I write up here?
NP. Oh no.
Oh, sorry, it's
NP.
NP.
Yeah. 237.
237, very good. Very good. Now in the exam, they won't expect you to look up the periodic table, so they'll tell you that you get neptunium and palladium at the end. Let's have a look. Yeah?
They will give us the the protons and the mass, everything.
Give us what? Say again?
For example, they will give us it's 92
Oh, you'll be given the mass of
NP or the.
yeah, if you need to know their masses, you'll be given them, yeah. Let's have a look at another one now. Okay. Maybe a tiny bit too easy. But I actually know where I have some good questions to practice. Well, you know what? Let's do one exam question where they have to make you balance something. Past exams, physics. Let's see, 2014. Well, they have. So, is it section A or section B? So in this year, the nuclear balancing was not in A, so maybe it was in B. There it is there. Okay. Right, let me zoom in. So you see, it's quite an easy question. So here's the one I want you to try. Now please notice, please notice that they gave you the material it becomes. Yeah, and actually, I have a bad habit of writing my numbers on the right, but you can see in the exam they put it on the left. What do you do in chemistry?
Right.
You put it on the right?
Yeah. Right.
Yeah, right now.
Yeah, but in your book it's on the left.
Yeah.
I should really have it on the left. But I got into the habit of putting it on the right. Anyways, it doesn't matter. It's top and bottom.
Which version is the number of the question?
Oh, this is version 1 of 2014. So look. They tell you that the radium becomes radon. Anyways, they also tell you that it's an alpha decay. So can you balance this equation for me here? Balance this one.
220, 86.
Hmm?
220, 86.
220 and 86, and what's the question mark?
Helium.
Yeah, that's what numbers. Write it down. You wrote it down? Great, okay. So let's have a look. What do you mean just a second? It's really short. Give it to me, Karar. It was or.
Or 220.
No, the first one was or A, was it? Or
Yeah, or A.
yeah,
224.
224 and 88 becomes.
Is 220. Or N.
Yeah, 220,
86.
86 plus helium
40.
42. Easy peasy, kind of, right? Let's have a look, see if we can find a more difficult one. How many marks do you think that was?
1 mark.
1 or 2.
free.
Can you do A7?
Physics? I
Yeah.
will, don't worry, I will. See what I mean by it being a good question?
Yeah.
3 marks is too generous. Let's go to 2013, have a look.
Two marks. So 13?
Let's see if it's there.
13?
Yeah. There we go. This one for 2 marks this time.
Scroll. Oh.
Something like
Okay, try this one now. So balance this equation. I don't even think they tell you what the AU stands for. Hg is mercury, isn't it?
Yeah.
No.
Yeah. Isn't it?
Yeah.
Maybe.
Which particle?
Which is typical?
So what's AU?
So to
No, no, no.
all.
Delta.
You don't think it's
Oh yeah, sorry. Yeah, well, which is it? It can only be one thing. What it must it be? Must be beta. Yeah,
Definitely.
must be beta. What is AU now? Let's see.
All.
No, I don't think it's gold, is it? Wait, is this actually AU is gold? AG is silver.
Silver.
Very good, sorry, Tekken, you're right. AU is gold. So this is radioactive gold that decays into mercury. Okay. Very easy, very easy question for 2 marks. Yep. Let's have a look at it. So, what was the nucleon number for the gold?
199.
198, and the proton number? 79. And it becomes mercury 198 80 plus an electron 0 minus 1. 2 marks, you know, it's really generous. I mean, it should really only be 1 mark. Let's.
What?
It should be. Come on now. We're barely using any brain power to do this. I mean, it's Monday morning after a week being off, you know, and it still feels too easy. Let's see if I got another one here for you to have a look at. So, remember I was saying that, you know, different people write the exam. So the person who writes the exam at the moment, he likes to give you a little formula and you have to fill in the blanks, whereas the older one, it kind of had more words in it. So I don't want to go too far back because I think it's more important to... I don't want to go too far back. Let me go back just 3 years. I'll go back here. Okay. Beautiful. So this is actually a question for 4 marks. So again, you see what, I mean, they tell you what the material is here. Yeah. So they also tell you that it's alpha and beta. Yeah, so I think we'll just do one more. We'll just do this one.
Which year is this?
Oh, what was this one? Let me check, sorry. It was
22.
2012 version 1. Okay, you got this one? So what's the number up here? This is 216 and this is
84.
84. And this is helium 42. And this one here, this would be 228 and 90. And this is E0 minus 1. So you know, like that's 4 marks. It's not difficult stuff. I haven't said this yet, but I'll say it now. So alpha radiation and beta radiation, they have different abilities to pass through materials. So in fact, something like alpha radiation is very easy to block. So with alpha radiation, you would just even need like a thick piece of paper like this, and you can block alpha radiation, or it will just bounce off of it. So alpha radiation is easiest to block.
Does it have to be thick?
It doesn't even have to be this thick. Like I think even a sheet of paper might even block it.
Yeah.
This would definitely block it. Beta radiation needs to be something a bit thicker. So
Aluminium.
yeah, like a sheet of aluminium, a sheet of metal, something like this.
Yeah, like foil paper.
Yeah. Gamma is extremely difficult to block. You would need like a meter of concrete
Yeah.
to block it.
Mm-hmm.
So that's what they mean by penetrating power. So the penetrating power and range of an alpha particle is quite low. And the answer would be alpha particles do not penetrate far. They can be easily blocked with something like a piece of paper. Beta particles have more ability to penetrate. It would require a sheet of aluminium, a sheet of copper, something like this to block it. And it doesn't say it here, but if it did gamma, gamma is the most difficult to block. It requires a meter of lead or concrete or something like this. So I mean, if we were to look at this question, there's some stuff here which I haven't done. Because you do chemistry, I don't feel the need to do it. Like for example here, what is the name for the A? Can you see? What's the name of the A? What's it called? Speak up, don't be shy.
Nuclear number.
Nuclear number. And what's the name of the Z?
Atomic number.
The atomic number. Yeah?
Yeah.
What information do these quantities provide about the nucleus X? So the A tells us what? The A.
The total of the protons and the mass and the
Neutrons.
Yes.
And the Z?
So yeah, proton
What is it?
tells us the number of
Come on, this is basic chemistry. This is chemistry week 1.
the number of protons.
Number of protons. Isn't it?
Yes.
Yes. So, we've done this part, haven't we? And we've done this part.
Yeah.
And we've done this.
Yeah.
So, how many marks have we gotten? 2, 4, 6, 8, 10, 11, 12. So, you see, you should have 12 out of 20. And yet, you'll still manage to screw it up. You will. You will, because you'll say stupid things like, this is the number of electrons, or it's the number of protons plus neutrons. And when I'm correcting it, I'm thinking, why did you say that? You just threw away like 12 marks here. So this atom question is, in my opinion, the easiest question in section B. You know, like already we can do half of it this year. Now I want to do some maths and some physics revision. You had a question for me, but just before I do that, I just want to show you last year's atom question.
It comes every year.
No, most years though, but none of the questions are guaranteed. There has been at least 1 year for each topic where it has not appeared. So if I look here at last year's question, not as easy. Most of it we can't do yet because we've only done 1 lesson on it.
How many lessons we need?
The atom,
We can finish this week?
No, 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 no. We won't go that fast. Come on. Ah, stuck. There's 9 topics in the atom.
So we can finish it next week.
I won't go too fast in this because it's the last topic, you know, and because it's the best question in the exam. I want everybody to do it and get full marks in it, you know, because a lot of people who do this do get full marks in it or nearly full marks. So we got 9. So what I'll do is I might just do one topic per double lesson. So we need 9 double lessons, and we have 2 double lessons in a week. Well, no, I'll do 3 a week. So I'll get it done in 3 weeks or so. Maybe a little sooner. Some of the topics won't need 2 lessons. But anyways, I have to give a double lesson to your physics exam. When's our next double lesson? Is it tomorrow?
Thursday.
We don't have physics tomorrow?
No. Or
Wednesday, I think.
Wednesday, I think.
Well, anyways, our next physics lesson will be a double, won't it? It goes double, double and single, isn't it? Just like the maths. No, maths isn't quite that. Maths is double,
Single, single.
double and 3 singles?
Yes.
So when's the physics exam?
So the physics exam is in the next class, the next double class. So I think is that tomorrow or is it Wednesday? You want to check, yeah.
This is tomorrow we have double maths
Yep.
and we have double physics on Thursday.
Okay, so your double physics on Thursday will be the test, 2-hour test.
Yeah.
And tomorrow, when you have a double maths, that will be your maths test as well.
Tomorrow.
Tomorrow.
Yeah.
So tomorrow we have Wednesday or something?
Yeah, Wednesday.
Oh, so what's the but like see that Wednesday see that the 6th and
She's
the
on the
class you
both
said
days.
this.
She's the both days.
So with math on Tuesday.
Tomorrow, yeah.
Tomorrow math.
Mhm. So I'll give you the homework next time in physics. What I want you to do is just get ready for your math and physics tests.
Can you do the drive thing?
Oh yeah, I'll do the dry thing after I do Tekin's question in physics or math?
Physics.
Physics, okay. What's the topic?
Transformer.
Great, so we're going to have a look at a revision question here, a transformer question. Let me just stop this.